Alright, hello everyone. Now let's look at problem 23. Merge K sorted list. You are given an array K linked list. You are given an array of K linked lists. Okay, K linked list. Each linked list is sorted in ascending order. Merge all the linked lists into one sorted linked list and return it. So we have, let me read the question to see if I understand it. I understand the problems. So we have case sorted linked list. And we would like to return merge linked list. Okay, understand the problem. Let's look at some example. So the first one, you have 1, 4, 5, 1, 3, 4, 2, 6. Okay. So if we merge them, you will have 1, 1, 2, 3, 4, 4, 5, 6. 1, 1, 2, 3, 4, 4, 5, 6. 1, 1, 2, 3, 4, 5, 6. Yep, it is correct. Second example is an empty list. Input is empty, so output is also empty. Okay. Third example, there is one list but it's empty, so return is also empty. Okay. So I believe I think I understand the problem. I would like to have, may I ask a few clarifying questions? So clarify. So K can be 0, which is obvious. And then, okay, how many elements in total? So range of K. And what are the size of all the linked lists? Okay, range of length. So here we are given that K is between 0 to 10 to the power of 4. And then the list length is between 0 and 500. I think all the others are not relevant. The sum of length will not exceed 10 to the power of 4. So we are given sum of length is bounded by 10 to the power of 4. Okay, so off the top of my head, I think there is one way we could do this. I think we could use a heap here for more efficiency, because we are given a sorted list of we are given k sorted list. And then what we can do is we take the first element of each list, and then we can put it into the into a heap. Heap would be just of size k element in the heap. So every time we remove an element, we take note of the list from which we extract that node, and then we we move on to the next node in the list, and then we could add. Okay, so let me repeat my steps here. But let me just write it down. So step 1 is heap of k. So I will create a heap of size k, and then I'm gonna insert the head node of each of the k lists, and then inside a while loop, repeat. I'm gonna do this until I have gone through all the nodes in the list. So I will pop and append. So I'm gonna pop the smallest node and then append it into my output. And at the same time, I'm gonna insert the next node of the one I just popped in this, and then by doing so, I would have one node at most in the heap from each of the k sorted linked lists. And in the end, I'm gonna get one list of sorted output. So let's look at the first one to see if we can use this algorithm. I'm gonna use heap. Then initially it would be 1, then left is 1, 2. Okay, so let me repeat. I will need to know from which of the list we got the node from. So let me just put it head. Let's call it head 1, head 2, head 3. This would be 1, 4, 5. 1, 3, 4. Then 2, 6. What was that? 2 and 6. Okay, 2 and 6. So initially, I would have 1. Sorry, 1 is from head 1, 1 from head 2, and then 2 from head 3. Output would be, at this point, we would have 1, and then when we insert the 4, we would have okay, so we would have 1 head 2, 2 of head 3. Hold on, how does it work again? So I kind of forget. Alright, so first of all, after we extract the value, one of the value must move up. So in this case, we would have 1 head 2, and then the left would be empty, the right would be 2 head 3. Is that how a heap work? Let me just review a bit about heap. Okay, so every time we push an element, it will end up at the it will be pushed at the end of the tree, and then it will move upward if it is smaller than the parent, and then we keep on swapping until it reach the correct position. Okay, and when we pop, we take the last element in the tree, put it in our root, and then we're gonna reorder the heap by swapping with the minimum between left and right until it reaches the correct position, and it would type are greater than or equal to 30. Okay, that makes sense. Yeah, so let's get back to our problem there. So in the first step, it will extract the 1, and then we pop up the 2H3 to the top, and then 2H3 will move to the left side. So now we have 1 head 2, left would have 2 head 3. Okay, since we pop up the header 1, we will push in another 4. Now we would have 4 right there, so yep, 1H2, 2H3, and 4H1. Here it will be 1, 1, Okay. And then we plot the last element, then move it, so we have 2h3 and 4h1. Moving on, we would have added a new element from h3, and we put in from h2, so we need to 3 from h2. Okay, so now we have 2h3. The left would be 2h3. The width from h2, which is 3, so 3h2. And now we pop again, you will have 1, 1, 2. Then we move on to 3, so we have 3h2, left is 4h1. h1, h2, h3, no, that is h2. Well, actually, 2 is h3. Yeah. Now we need to add something from h3, which is 6. So 3 from h2, 4 from h1, 6 from h3. Then this would be 2. Again, like that. 1, 1, 2, 3. h1, h2, h3, h2. So 1, 1, 2, 3. So far, so good. Then the 6 will move up and then move down. So we have 4h1 and 6h3. Okay. 4h1, 6h3. Now something from 3 is our node. So we now work with two units. This means we would have be able to do it faster, because h2, h2. If we take something from h2, that would be 3. Okay, so 4h1, 6h3. Sorry. So 4h1, the left is 6h3. Now that there are only 2 of this, wait, 4, h3 is not done yet. Okay, h1 and h3. Sorry about that. Let's continue. Where were we? So 1, 1, 2, 3. Now we have two string left. This would be, let's see, 1, 1, 2, 3. So 3 is from H2, so there is still element from H2. Don't forget about that. H2, we have 4. So for H1, the left is H3. Then for H2, now we remove 4 from the first one. So we will have 1, 1, 2, 3, 4, where the last 4 is from H1. Then it should be for H2, 6, H3. Okay, so now the first element again, the first string again. The next that we have from H1 is 5. So 5 would be, yeah, it does looks good. And let's see, then we have 5 from H1. So 4 from H2 is the next thing. Yep. So now you have 1, 1, 2, 3, 4. What does it gonna look like? 5H1, the left will be 6H3. Okay, 4 is from H2, remember? Now H2 is now done. So what do we do now? Then we just sort the rest of it. Then I think the rest are straightforward. 1, 1, 2, 3, 4. And then 5 would be replaced by none. Then we would have 6. 1, 1, 2, 3, 4, 5, 6. Alright, so how are we gonna do this? I think in Python we have heap queue. So we could do heap queue. But I need to check the exact way to use heap. Python heap queue custom key. Yeah. So how do we use custom key in heap? Okay, so we need to, then we can't do anything here. But yeah, so we are asked to override the class definition, in the list not definition, which I don't want to do. Yeah, I think there is no other way. Let me see. Okay, looks like I need to, I must create a new class. Okay, anyway, let's do that. So class, I'm gonna call it new node object. Okay, let me just directly code it. Anyway, let's just do it here. It's not an issue. This would be list node. Hold on. Okay. So self dot not equal let's just call it not here. So this will be of type list node. Let's call it not define. So here is what we need. Representation of self. This will return self dot node dot form. And now the other one that we need is iterator. Oh, no, it's actually less than. So less than self other. Okay, how do we do this? We need to return self dot not dot form less than other dot not dot form. Now heap would be the let's see. So the input is okay. Let's just put the whole list there. So this now we need to heapify it if I'm correct. Yeah. So heap the heapify. Q.heapify heap. Right. And then I'm gonna create a new head. How am I gonna do this? Let me just do it in the next page. So now you're gonna have head. This is for our output. Gonna create an empty node. So while here is not empty, I'm gonna do let's see. Okay, so I think I need to use the curve to keep track of how far we are in our output list. So now while we heap heap.pop, is it? Hit q.heap.pop of heap. Right, so curve.next is the pop of it. Q.heap pop of heap. Hold on, so how do I push it? Okay. Python heap push. Okay, so it's heap push of heap of item. Okay. Now I move on the curve.next. Then I will need to push it back. Okay, so don't forget to check if it is still a node. If curve.next, then I'm gonna put it inside heap q dot heap push of curve.next. And then in the end, sorry, I think I need to put in the heap again. Heap, yeah. Gonna return the head. Okay. Cool. Let's try to run it in LeetCode. sorry, let me go through the code again to make sure I didn't miss anything. First, I'm gonna create a heap of everything, and I'm gonna create our output. Sorry, the output should be head.next. The output head, I initialize it is as an empty list. Sorry, what is the output again? Okay. Okay, so and then I'm gonna use another variable called cur. Cur will keep track of the uh, the last element that we inserted so that we know where to append the next node. Oh, the next node that will be part of our output. So while heap is not empty, I'm gonna extract the node, the which is also the head node of uh, of one of the input linked list. Then I'm gonna, because I have just appended a new item, I need to move the cur to the latest node, which is cur.next. And then, because in this case I'm appending the whole linked list to cur, but I'm not sure whether the rest of it is the correct order, so I need to push it back into the heap so that it will take care of the sorting, and the next time we pop, we will get the smallest item. Okay, so if cur.next is still is not, then we push it back. Then we keep doing that until the end. We return head.next. Okay, let me try to. Now let's look at the examples to make sure that it works as intended. First examples, again, we would have 1, 4, 5, 1, 3, 4, 2, 6, and then we would have 1, 1, 2, we extract, then put it back, 1, 2, 4, extract again, put it back again. Now we have 2, 4, 3, extract again, put it back again. In the end, all of the input will be empty, and our heap will also automatically be empty. Then we return the output. So I think this should work. Let me try to put it into our code. So first of all, we create another class new node, find init self the node self.node equals node. Then also need the representation can I just use the LT there? Let me check real quick. Turn hit Q custom key. So what they need. Okay, so we need the LT only. Yep. So to save time and our coding, I'm gonna use LT. This other return self.not.val is less than or equal to other .not.val. Okay. Now this is the main part. So heap would be the list. So for head in list, I'm gonna do new node. I'm thinking whether there is a better name. I think I should call it new head. Or I think just head. So I'm gonna create the head. Head. I think better name would be head node. Sorry about the confusion. So head node head. Or head in list. Then hit q.heapify. The heap, the heap, yeah. Then where heap, gonna do, don't forget to initialize the cur is empty node. And the cur point to head. So while heap cur.next equals heap q.heap pop from the heap. Yep. And then we move on the cur. Is cur.next. Then we append it back. Q.heap push heap comma cur.next. Then we return the head. Let's try this. Hit Q. So this is hit Q. Head node has no attribute next. Ah, right. So what happened here is that after I append the last element, I should not move forward. Is that the case? Okay, I think I got it. So I think I'm doing it the wrong way. Yeah, I think probably I could override the class definition to aid me. So let's try to do that. Let's not. Is it possible? Let's see. Yeah, no. So let's try it. Oops. I'm gonna comment out the whole thing. Yeah, let's do it here. Let's see. Run. Head node. This node. Okay, so here it should just be list. So what is the error this time? Less than is not supported between instances. Did I have said it here? How about self dot node? Okay, so looks like I cannot override the class definition. Now let's move back to our solution and try to figure that out. Okay, so in here, essentially what I did is the list node would point to the node. Okay, so what I need to do is instead of the head node, I'm gonna call it the node. So when curl move to the next, instead of appending this, I'm gonna use the head node. I think that makes more sense. So the heap will store the head node instead of list node. Curl.next. Okay, here I need to check if head is not okay, then just if head is enough. Okay, case one. Oh, okay, I forgot to return the next. Alright, let's try to run it. I think I could get it wrong. Let's give it a shot. Okay, I got it right. Yep, I think that's about it. It took me some time, but yeah, just trying to figure out the best way. So let's look at other people's examples of how they solve it. Ray got a pen. Well, this is the sorting. Is this? Looks like this is creating a new list instead. Yeah. Okay, how about this? Result. Yeah, this is also creating a new object. And this one is just it's extracting all the nodes and then sort it. Well, that would take n log n. So that is a bit inefficient, I think. Well, from my solutions, I think this would just take like let's see. Then the sorting itself would take log n. So total that would be on log k time, and then the space is ok. Yeah, because my chip size is just k element compared to the other solution where we append all the list into any other list node into an array and then we sort it. That would take O and log n. So I think that's about it. Thank you.